the fabulous Rick Collett. I'm going to leave
thank
him
you.
to talk.
So James asked if I would present on unexpected things that we run into in restoration projects, and I struggled with that a little bit. Probably more than a little bit, because I spend a lot of time telling clients there are no unexpected things, that we've got it all sorted out, and that they shouldn't expect that we're going to run into things that we don't foresee. This is where we're from. We're from about 3 hours west of Chicago, about 30 miles east of the Mississippi River in Illinois. So what kind of things do we run into that are unexpected? And I started to think about that a little bit. I mean, granted, there's always like a piece of wood that you miss or might not, anticipate just how rotten portions of a building might be. But the really big ones for me have been things like tornadoes or derechos we have now. Derechos are fairly new. They're straight line winds. So termites have become more and more of an issue in the buildings that we're working on. We also have carpenter ants and of course powder post beetles. And carpenter bees now are moving north, that's right. And they used to not really be a problem for us. So as the climate has changed, now we have more wind, we have more rain, which in turn released more flooding. We have more insects that are damaging the buildings that we work on. And when I was doing this presentation, as I started gravitating towards this work we're doing with LiDAR and polygonal and round barns. And so I omitted all the rectangular and square and other buildings. So other than a bridge, I do have a covered bridge in here. So I'm going to show you a lot of octagonal and round buildings because I thought you might find it interesting. And we live in an area that during the Industrial Revolution, agriculture was huge and there was a massive amount of immigration from Europe. And so people were pouring into this part of the country. And like I said, it's a huge area. And Illinois and Iowa are both about the same size, and they're basically the grain belt. And as people started pouring in, as immigrants started coming from Europe, they were putting up farms everywhere. The Industrial Revolution was going on, and people were changing buildings. Scientific barns was this idea that was presented to farmers saying, you don't have to build these big rectangular heavy timber frame barns anymore. Now you can build these kind of things. And this lasted for really from about 1890 to, let's just say 1930s, just to be fair. Certainly before, a little before, and a little bit after, but we're talking about, buildings like this on a magnitude of hundreds of thousands of them being built. Polygonal, round, Gothic arch, laminated, clear span buildings. In Illinois, prior to this, there were 350,000 timber frames already before they started putting up these buildings. Now, almost 90% of those buildings are gone now because there's been a massive depopulation of rural areas, like where I'm from, massive depopulation. So with that, buildings have just been kind of left. Almost all the buildings I am going to show, in fact, almost all of them, are buildings that were left behind during this exit of people over the last 30 years. So this is one of them. And just to give you a sense of scale, that's that building on this farmstead. And that's not a small two-story house at all. It's a big octagonal building. It's a dairy operation. And what we started doing about 4 or 5 years ago is we started scanning things every once in a while. And over the last 18 months now, we've scanned everything. And we not only scan big things, we scan small things. And I use that as a tool to basically try to prevent us from getting into situations where things are unexpected. So I'm showing this just because I thought it was kind of interesting. I'd chosen to lift this one from the outside. So it's 80 feet around, and I just clamped I-beams, H-beams actually, all the way around the outside and lifted it and supported the center. It is a clear span. I hung the center actually here with a drive bay. The centerpiece here is a drive bay. There's a big hay yard arm at the top. But what the scanning does is I can get into a job like this and not have to worry about what I'm going to run into, because when we do a scan, it's not me sitting there setting up a folding table with tape measure anymore, drawing things, and then trying to take that and give it to a draftsperson who's never worked in the field or maybe has worked in the field, but still you have to get that whole language going. Part of what we've done now is we've integrated our scanning with density killing. and it's all about trying to eliminate unexpected stuff. And I want to be able to go to somebody and say, on a building like this, you know, we knew about this Raptor plate damage, we knew about the Raptor damage, and here's our proposal to do it. And one of the things I've sort of said in business, or one of my mantras for my own business has been, I don't do change orders. I don't do change orders unless there's a scope change. And I don't want to do change orders because I missed something. So I try really hard not to miss things. And, you know, sometimes we get into doing some engineering. I threw this photo in because, you know, we've got this tension rod and a steel king post to reinforce these purlin plates. But they are generally, we're trying to do fairly simple repairs. We also work on covered bridges. And so I threw this in here because I wanted to talk about unexpected stuff. And you can see we've cribbed this building up. It's 167-foot span, and so this is a burr arch truss covered bridge. Covered bridges, they get loose, and so you have to go in and replace this lower cord member. You have to replace these wedges. Sometimes the bolting starts to rust, so we go in and replace the bolts. You can see here we've replaced this lower cord member on this bridge. And I've also pretty heavily invested in jacking systems. So a big part of what I do is lifting fence. It doesn't have to be a big system. I don't actually have a unified system. A unified system is where you can put 24 jacks in this building and push a button and the whole building goes off. So that's a much higher scale than I work at. Where it's really handy is when we need to lift sections of buildings, whether they're masonry or wood or something like that. And so we did the lifting on this building, and in this particular case we blocked up the river, and we put in a couple of shipping containers for a culvert. And we've got a bunch of concrete blocks kind of lying around, because one of the things that bridges do is they move like this. They distort like this a little bit. So a big part of our work is replacing X bracing in the bottom of them. So the concrete blocks aren't there to anchor this building down in case of a flood. They're there because we're using them as dead men to basically tweak components of the bridge. They weren't meant to stop this kind of level of water that's now coming at our bridge. You can play this video. So this came as a text message to me.
There's our box, it's our jack, the roller, the concrete block getting ready to go. It's now underwater.
So this river came up 19 feet in less than 24 hours. Whoa. And it got up to about this high, and it washed out our cribbing towers about 12 miles down the river to a lake, and they floated down the river to the lake, and I had them all screwed together. So we rented a pontoon boat, and we went and recovered our cribbing, and we put it on a truck, and we brought it back and finished the job. There are a lot of different ways to fix bridges like this. You know, we weren't jacking up this whole bridge. We weren't moving it. We were putting camber back in it. The camber had fallen, so it had been reverse camber. So we lifted it up about 2 feet to put camber back in it. We replaced the whole bottom board. We tightened everything up. So I don't really know where we could have done this particular job differently, but a very unexpected situation. This is a 55-foot or 60-foot round barn. So I'm gonna show some of these images because I thought you guys might find them interesting. And these round barns, I think there's probably a couple thousand left now in the Midwest, I would bet. And they were really promoted around 1895 to 1930. Universities in our area all built them as dairy barns, and they often look like this. Some have a central silo. This is a silo made out of cypress wood, and some of them are clear span. They all have pretty common failures that we see. And so when I went and looked at my first round barn, the first round barn I did was about 15 years ago. And of course, a lot of things happen when people build buildings. The first round barn I looked at, all the lower walls were built out of beautiful, clear, straight grain Doug fir. But the entire upper roof and what we call the midspan furling plate, which is in here, was made out of cottonwood. And of course, it doesn't do well with water, and it rotted. So we lifted that particular roof system out and straightened it out and rebuilt the midspan purlin plate. But Generally, they're built out of fairly high quality wood, and they don't have a lot of redundancy built into them. And they all tend to, unless they've got a lot of bracing, they all corkscrew. So they all corkscrew up to a couple of feet, and they tend to rack a fair bit, which is what the scans I'm going to show you look like. A lot of times they all look like this down in the basement. They tend to be concrete or concrete block from the 1890s to the 1920s. This is when the bulk of them were built, you know. And they were patented in Indiana and in Illinois by a man named Benton Steele and promoted kind of all over the country. But the beautiful thing about these scans that really help us deal with this unexpected situation, which was really what James asked me to talk about. Like I said, I struggled with. You know, like I can look at this scan, I can see the building's racked. And I can walk around a building like this all day long and look at it from a different perspective with my eye and maybe see it, maybe pretend to see it, maybe not see it. We're going to scan this, and I'm going to use this scan as a threshold for this conversation. Now we have some data. And not only that, we've got some data that we can use if we get the job. So we can document a building being somewhat racked. And you can see it a little bit here in even this image. Because if you orient the scan right, you get level and plumb. And I can use that when I cross-reference other data that's going on. So this just happens to be our repair. So this talk isn't about how we repair buildings. It's about how we present this information. And so I don't get a lot into the repairs, but this is a very, very typical repair for a round barn, where we're putting in some kind of lateral member, we're putting in some gracing, because what happens is these buildings get smacked by the wind, and they distort, and they go egg-shaped, and the whole thing leans over this way or that way. And so you'll see that as we kind of go on. And this is a pretty typical round barn repair. And I want to say that, like, in this work, you know, we're not trying to replicate. We're not necessarily trying to turn these particular buildings into museum pieces. What we're doing is dealing with a large inventory of buildings that we're trying to keep upright. And we're trying to do that in the least invasive way possible. So the idea is that with these interventions, that we're damaging as little historic fabric as possible, removing as little historic fabric as possible, and we're coming up with solid solutions that work over and over and over again on this style of building. So this is a common chevron and common brace and sort of lateral bracing system in one of these buildings. I'm going to talk a little bit longer about this building. This is the building we have going on right now. This is a 20-sided structure. And again, with planning, I think about different ways to lift buildings, and in this particular one, you know, I thought about using I-beams and cribbing towers from the outside. You'll see ultimately how that evolution changed into something else completely. And I think that it's probably important to understand that, like, because Illinois and Iowa, northern Indiana, northern Missouri, southern Wisconsin, and southern Minnesota, they're all pretty much the same landscape. And it's all heavy glacial deposition. So in some cases where we work, it's 100 feet to bedrock. There's no stones. There might be some glacial till on the surface in some places, but there's hundreds of miles where there are no rocks. And so a lot of these buildings I've worked on have very, very poor foundations or no foundations, or somebody just like rolled a rock underneath one corner of the building and that's it. So what happens, of course, is that the buildings start to sink into the prairie. And they start to get distorted and they start to rot, and that's what happened to this building. So this is that project before we started, and here's the scan. So we started, I actually started working on this back in 2008 before we had any of this technology. And a couple of years ago, the client started to get a little bit more interested in doing the work. This is a municipality that owns this. And so we scanned it, and then from that scan we create a model. So we take that right to a 3D model, and at that point then we do engineering and stuff like that. Once we understand buildings' use, so of course a lot of the buildings I work on, there's change of use. We're going from agriculture to commercial, so you got to deal with floor loads, wind loads, snow loads, seismic sometimes. And probably, like, I think this is probably the most important thing I'm getting out of scanning. And what this is a slice through the first floor elevation. And what it's doing is the red is telling us where the building is low. So the red is at 7 inches, and the dark blue, I think, purple is 0. So we can look at this 100-foot diameter building and we can take a slice through a couple, and we might take a couple slices through because you can get bad readings because joists can be different heights. You can have different things going along with the flooring, but we can slice through the building and we can create these elevation maps. And let me tell you how this changed the bidding process, how it changed this whole job in a way. Because before we had done this, I had chosen not to lift this building because I only had personally enough steel to lift half of it at once. And to lift a 100-foot diameter building, you kind of want to do it all at once if you're going to do it in iron. And then when we did the scan, I started thinking about it differently because the scan allowed me to rethink how it was we were going to do the job. And it has this particular...
And also shows a picture to the client.
Showing a picture to the client so that they understand, because you can walk through an old building and it's like, oh, this is up and this is down and this is out and in and all these kinds of things. But when you can show it and you can slice right through it, you can mitigate a whole bunch of unexpected things that come up. And it you know, we use it, of course, when we get into foundation work. This building had 48 internal posts. We use it when we get to doing the joist work, so we reinforce this floor from 40 pounds to 100. We use it when we get into doing modeling. So all this information is coming from that scan. All these three-dimensional drawings are coming from this scan. All the engineering that we did comes from it. So it's just a shot of the roof system. I think this is about 55 feet, the upper portion across. And this is the main upper roof system. And we didn't have to do a lot to this building. There wasn't a lot of engineering required to the frame. We needed to do a little bit of reinforcement to the trusses in the upper level, but that was about it. And we played around with a couple different ideas. This just happens to be a drawing of one of them, and ultimately this is really all that building needed. Were a couple of upper principal rafters, or upper forwards, on each 20-sided diagonal beam that runs to the center. Just a little shot of our engineering calculations for the floors. So I prefer that we do our own engineering and our own repairs, and we do our own drawings. But this is all that prep work. It's the scanning, it's the drawings, it's the preliminary engineering done by our team or our subs in the preliminary drafting, all from that scan. And has anyone heard of plank on plank or stacked plank or board on board construction? Popular in the northeast Ontario, definitely around Chicago. It was promoted as a way Islay walls for dairy barns. So these are stacked 2x6s. All the way around this 300-foot perimeter. And of course, this is a ground barn, so it's sitting on a few rocks in the dirt, and all those walls sucked up moisture. And of course, it doesn't hold up real well when the windowsills fail. So we just took them out. And like typical, we put a foundation in underneath this building, because that's what most of these buildings lack, is any kind of serious foundation. We shifted from using a lot of cribbing towers and steel, which is really stable, to using shoring columns. And that's what these are. These are 10-ton shoring columns. So in that shoring column, you put a 5-ton jack in this side, a 5-ton jack in this side, a little hand jack, and the building goes up like that. We used 40 of them in this building. And the blocks are here to anchor it down. Those are the shoring columns. So that's how we ended up lifting it. And we lifted that building in 2 days. 100-foot diameter building, 2 days. Of on-site work to lift it and take it to zero, from 7 inches out of level to zero.
But you've only got those pinch points that you're lifting, right?
Yeah, so there's a ring beam. We were lucky. There were 2 ring beams in this building that we could grab onto, and it's where the joists met. If it was something else, yeah, it wouldn't have been possible. But
That's the difference between 200 grand and 4 ton.
that's it. And I think it was doing the scan that like made me just think differently. That's all it was. It gave me another tool to think about the job differently. So a panoramic view of the lower level and the framing that we ended up doing around the outside, a stick-built wall. This is the upstairs haymow. This is half of it. And this is actually just a few days ago. So like I said, the idea is to be able to, was a $1.8 million job. And I don't expect to have change orders. I expect to be able to walk into this job and not change order the client because I missed a rotten piece of wood somewhere. That we dealt with everything that we thought was unexpected, was expected, except the stuff I can't control, which is the wind and the water and all this other stuff. I did show this one last year. This is a 103-foot diameter round barn. And I thought I'd bring it back because I wanted to show these scans. Again, this is the biggest round barn in Indiana. It's 75 feet to the peak. And if you look at these scans, they're super telling. So the client calls you and says, oh, you know, my barn got hit by a tornado, and do you think you can fix it? And I'm always like, sure. And he's like, I think it's leaning, you know, this way and that way. So we can scan it, and we can see the lean. And I think you can see the lean if you look at it. And you can see that the roof is misshapen. And so from that scan, then we start to come up with these strategies. So we can walk into this job, which is a $700,000 job, no change order. No change order for anything that went on in this building. Everything that we dealt with was anticipated. And like a lot of the buildings, it's about putting something in there to basically add spokes to the roof system. Think about it as a wheel with no spokes. That's what these round barns end up being, wheels with no spokes. They get smacked by something and they get misshapen. And we do chevron bracing. This is looking at it from the inside before we did the work. But a lot of chevron bracing in the roof. This is the inside. And in terms of like elm, which is also one of the conversations from yesterday, there's a lot of elm where we are, still is. These are 36-foot 8x8 elm posts right here. That's kind of give you a sense of scale of this building. And they're all, of course, you know, distorted because they're loaded and they're not cross-braced. So a big part of our work is cross-bracing this stuff in these round buildings. So we brace these long struts, and we put in these connectors to this derrick tower. A lot of these round barns have derrick towers. So these are 37-foot long, 14-inch LVLs that are sort of stiffening up what some people call an upper plate or a midspan plate, purlin ring. This barn has two of these midspan purlin plates. Some buildings have 5. Some of the fancier ones will have 4 pitch changes. This one I think has just 2. And then again, you know, lifting this building, putting a lower wall system underneath it and a foundation. So when we took this foundation out, it really was just gravel below the stick building. Just really no foundation to speak of. Yeah.
I don't know if you got this at the beginning, but why did they build them this big and round? And what was?
Well, this guy wanted to build one bigger than his neighbors, which was 100 feet. So he built it at 103. But number one, you've got a massive wood resource, massive amount of wood. And number 2, you've got the Industrial Revolution going on and a fair bit of wealth. Number 3, you've got farms expanding like crazy because the Midwest is blowing up. I mean, it's totally blowing up. And so you got massive amounts of hay production. So they were shipping hay from where I live down the Mississippi River to New Orleans, which is 900 miles away, all the way through the Gulf of Mexico, still the Gulf of Mexico, by the way, around Florida and up the Atlantic to New York City is where hay was going from where we live. So this is a hay barn. And they also built things called hay press barns.
Was there another real size and shape? Or was that pitch to get?
It's literally hay.
Just pitch to hay.
And they could do it.
Do they sometimes have cows below?
Yeah, this one did. Almost always they have a basement. They have a lower level and either dairy or livestock. You know, one of the problems with the Midwest was that European animals didn't work in the Midwest. They did okay on the East Coast, but they didn't work where we live because of the massive temperature swings. So one of the reasons we see these big buildings is actually because they were dealing with European and livestock from the eastern side of the country, and the livestock were just dying like crazy. They couldn't handle the winters, they couldn't handle the temperature change, and so they started cramming animals inside of buildings. Of course, they all died too. So then they stopped building these big buildings to put animals in because, you know, it was muddy and not healthy. And then as animal breeds evolved, then you didn't put animals inside anymore. So it's partially animals and it's partially hay.
But who would have built them? What's the?
This guy owned the newspaper in Indianapolis.
Would they have been like Scandinavian origin?
Well, so where I live is the largest Swedish immigration in the United States. So you have Swedes coming to the Midwest was settled initially by the French, and then later a few Americans came along. But the bulk of the settlement is Czech, Polish, German, Swedes, Norwegians, Finns. What am I missing? Italians, of course. They all stayed in the cities. Irish and Germans. Irish stayed a lot in the cities too. But the Germans, Poles, Czechs, Swedes, Norwegians, and Finns all moved to the countryside. This guy, I don't know where they came from. He might have been in America.
And anything hand hewn or?
No, this is all sawn. It's all sawn. Yep.
So it's just speeding the economy, right? You just got to get something big up quickly.
Big, quickly.
Yeah.
And it's because animals were dying and hay was selling like crazy.
The population was saying.
Population was blowing up. Like, I don't know how many immigrants came out. Millions and millions and millions of people came to the Midwest from Europe all at once. And so you had labor, you had resources, you had a market, you had a way to move goods to market because railroads were blowing up. It was just a perfect storm.
Wait, do they have a crane inside? So it's asking them.
What's
Do
that?
they have a hay crane?
This one, like a derrick or something, this one did not, but it's got a circular track right here. You can just see this iron track, and it's got 4 trolleys on it. So that you don't have to run the trolley all the way around. You can go to one side or the other.
Tongs or something underneath.
Yeah, tongs, or some of them have like a rope and wood frame that sets on the rack and then it picks it up like a... This guy told me that when his grandpa worked here, they always kept 2 years of hay in this building. So it was 2 years worth of hay in case they had a bad year. So that's probably another reason.
Yeah, the Bible.
Yeah. 12-sided building. I threw this one on here. We haven't done any work on this one because, like I said, we do a lot of consulting. This is how it looks today. And this is our scan of it. And this was for documentation again. This one's in pretty rough shape. You know, it's got a pretty, it's doing that kind of thing. And so we came up with a shoring plan. So a big part of our work is writing shoring plans to save these buildings until someone can maybe do a full-on restoration. This just shows where we took the scans. So that's how many scans we took in this building. I didn't really intend for this presentation to be about scans, but it ended up being about scanning because I figured out that over the last 3 or 4 years, this is how we've been dealing with unexpected problems in a way that I never dealt with before, and it changed my thinking. So we can slice through the building like this, which is great. And with that, if I don't want to draw, if we don't want to turn it into a drawing, sometimes what I'll do is I'll just mark that up. Okay, so I did include a rectangular building. So this is and I did because I wanted to show density drilling. And so we talked about termites, which are terrible. Carpenter ants. Carpenter bees, you can see where they go in. They can really make a mess out of stuff. But the big ones for us are termites and carpenter ants. And so this is like a 12 by 12 hewn oak post. And what I like about density drilling is that we can keep the density drill as a job site. We can take it with us wherever we're going. And if we want to know what's going on in the timber, all we have to do is drill it, and we get that as an instant result right away. So once you understand what the baseline sort of hardness is for the wood that you're working with, you can start to see where the pockets are. And you can, after you run it 20 or 30 times or 50 times, you can see where, okay, this is a knot, this is a dead spot, this is an internal check, this is something like that. And it allows me to understand what's going on with something like this. And this is a 12 by 12 that's like 14 feet long, and I could pick that up and put it on my shoulder. But when you looked at it in the building, it's all good. Looks great. You tap it, okay. But it looked great, but it's full of carpenter ants. And that density drilling allows us to deal with something like this, which is completely unexpected. And it's literally like, no more than like a drill guide, right? It's the same size as a drill guide, and it fits in a case this big. And that's the scanner that we have, a Leica scanner we bought 4 or 5 years ago. I'm using the scanner for something like this. This is a mill that we were working on, and so I can anticipate where I want to lift the building. If I want to work with a subcontractor and I want to tell them, okay, I don't want to lift the whole building, and why don't I want to lift this whole building? Well, because if we lift this whole building, we're going to have to do a whole bunch of foundation work. We're going to have to disconnect the sprinklers. All the electrical is going to have to change. All the plumbing's got to come down. We're going to have to deal with, leveling out the foundation, all because they're worried about this little area here in the center. And so in terms of reducing cost, we can go to someone and say, we actually did this one in-house. I didn't hire it out, but we can deal with it and say, okay, we're just going to lift that red center right there. That's all we're going to deal with right here on this floor. And that happened to be where the water wheel was, below it. And what I find with a lot of these mills is that, multiple flood events over the last couple hundred years, everything gets washed away, the building sinks a little bit, and they just stick some rocks back in there. And then a flood event comes again, stick some rocks back in there. And so that's what's going on here. The water's coming from this direction, it's coming through the mill this way and going out the other side. And over the last 200 years, it settled 9 inches. Look at that. And I like these scans too, where we can like zoom into the building. And super useful for Zoom calls with the client, because we can pull this stuff up. And if we look at it through Matterport, we can walk through the whole building with the client on the Zoom call before we've even had a site. You know, while we're still negotiating price, while we're still talking about, why is this a $500,000 job? Well, it's because of this and this and this, and I can walk people through it.
It's really surgical, isn't it?
It's totally surgical. And I think that that's what's happened, is I feel like I always had this kind of surgical approach. The first big restoration job I did on my own was 25 years ago. And we had a 120-foot long building. It was 48 feet wide, had 24-foot sidewalls, and I just split it right down the middle. And I took the whole right-hand side off, and I scalpeled it up the other side, and we put a whole new wall on that side in this very surgical way. And I think that's been our approach from the beginning, is to have these very surgical approaches to the restoration work, where we're trying to save as much historic fabric as possible, coupled with the fact that we're trying to save as many fillings as possible within some sort of budget constraint. There's always a budget. And with this now, I can actually like point to this stuff. So it's totally game changing. I threw in this Gothic arch. This is one that theoretically we're going to move this year. But I just thought you might like to see it. There are lots and lots of these around. These are generally glulam. They generally are from the 20s, another really robust time for building change. And it's 37 by 60, I think. And again, here's our scan of that building. And so in preparing for this particular move, you know, we don't have a lot of unknowns, but it'll go down the road. You know, we'll pick it up off its block foundation. We'll tear the blocks out. We'll set it down. We'll put it on a set of dollies. We'll drive it 13 miles down the road and put it on a new foundation. This is what it looks like on the inside. So a lot of these are pure span. Idea to get, you know, people were really down on having posts in the middle of spaces. They really wanted to have clear span for hay storage. And it really started with these hay trolleys that were patented in Illinois and Iowa around 1860, where you couldn't have tie beams in the middle of buildings anymore. You needed to have this trolley and this crane, and that all became obsolete in the 50s with hay conveyors. That's a cross section of this particular building. Again, very useful in talking to the client, very useful in talking to subcontractors. So I would sub out this move, yeah.
You mentioned glulam.
Yeah, it's glulam.
20s.
Yeah.
Would that have been like high glue?
Yeah. Yeah, I think so, because a lot of delam made.
That's amazing. Right, you go. I'm an expert.
Yeah, this one's okay. But generally speaking, our standard for glulam from that time period is just to screw the crap out of it.
Sorry, the big down screw.
Yeah, I'd screw it. Well, so down here in the lower level, a lot of times in the 20s, it's a timber frame first floor system with like a glulam arch on the top. And a lot of times there's glue failure in those things. And so generally, there's a couple of things we do with these actually. One is that they don't have a lot of, almost no bracing in this direction and wall direction. So one of the standard prescriptions, cheap prescription, is to run 2 sheets of plywood down the eave wall on both sides to provide a little bit of shear. The other thing is to come in and screw all the glue lamps with screws, because we anticipate glue failure.
Would they originally screwed as well? Like just right, okay.
Yeah, not nail lam or anything like that. No, these are glue lam, but in terms of anticipating a problem, so you go to lift this building and maybe you're moving it around and the glue starts to fail. I just anticipate that it's going to fail and I screw it ahead of time. I just screw them all. Screw them and add shear walls is what we do for most of it. And the way most of these are designed is they're really designed for that rafter to come down and fasten really securely to the joist, which is fastened really securely to the plate. And so all that needs to stay as a system. So another of our reinforcements is to reinforce that connection, because a lot of times that's where there's been water intrusion and there's been mechanical failure at the joist to rafter connection. So this is anticipating stuff that happens all the time. I'm not going to walk into this job and be 3 months into it and be like, oh gosh, what, all those bolts down there are rusted, you know? It just doesn't fly with people.
One of the joist rafter connection, like bolt.
Yeah, usually a bolt, sometimes a bracket. If it's like, it could be a bracket that's embedded in torque-filled concrete block, or it could be a bracket that's fastened to the plate down there, and it's joist to rafter, essentially joist to rafter connection. So I think this is my last one. This is a 20-sided, 148-foot clear span building that we did that had that sort of thing happen to it. And again, you know, I've only seen 2 buildings in my life I can't save, and they weren't really much of a building to begin with. But, you know, a lot of times the places I go, people are really divided on whether or not they should save them. And I would be frank in saying that, you know, in the culture I live in, saving buildings is not a priority for people. It's not something that's first and foremost in their mind. And in general, people see buildings as nothing but an impediment to a Dollar General. So, you know, does anybody know what a Dollar General is? No. Because nobody laughed at that. Not a single person got my note. It's a really crappy store full of stuff that costs $1 from China. What's that? Yeah, there you go. Calm down. So this is the Chautauqua building, and again, we did density drilling on it. And I think the thing about density drilling, again, is that I don't have to take these trim and this siding off the inside of the building. I don't have to pretend like I understand. I know what's going on in it. Like, we can really drill it and just figure out. And so it's like...
Explain how the posts are inaccessible.
Yeah, so the posts are inaccessible because it's cladded with like TNG, and then there's a trim board over that in each post location. So there's 20 posts. So do you drill it, or do you take all that stuff off and then go around and knock it with a hammer and pretend you can find dead spots? You know, no, we just drill it. We just drill the whole thing. It's less than an 1/8 inch bit. So it's a I think density drills are cheap, inexpensive tools that are somewhat invasive, but not as invasive as other things. I can leave all this stuff on the building. I don't have to take it off now. If we've got a rotten sill system in a building that's covered with, you know, water table board or clapboard or something like that, I don't have to take all the material. I just drill right through it, which is great. So that's what we're doing here.
How deep's the drill? How far can we go? Oh, wow.
Yeah.
Is your drill an independent unit, or does it actually speak to a data system? So
Yeah, you can plug it into your laptop. You can read it right off of the display, but it takes it and you put it in a spreadsheet. And then you can track it, and then we overlaid that density drilling with the scan. So the same guy, in this particular case Josh, would do the density drilling and do the scan, and then he goes back to the shop, and then he overlays the density drilling with the scan, and so now we have information about elevation and wood quality all at the same time. If we're doing more complex buildings that are like mills and there's more wood machinery and all this kind of stuff going on, super useful there. It's just a little bit harder to document than a building, but we use it the same way. A scan of this building again, it's a 148-foot clear span, and the scan on this particular case informed us about how we were going to support the roof, which is this structure. These are 90-foot long rafters, I think, something like that. I mean, they're laminated, but they're 90 feet. That's 90 feet from here to here. And so we had all kinds of failure going on, and I did happen to build my cribbing tower right over a storm sewer that backed up. So it was a bit of a skating rink in the wintertime. But in this particular case, based on the scan and all this other stuff that we didn't dismantle the whole building to save it. I mean, it was in bad shape. Like, roofs were caving in. Ultimately, the plan was just to support the king post, which is 30 feet tall, in the center of the building, and then surgically work on each section of the building without a full dismantle. So there are a lot of buildings, you know, I don't know, taking like 100 down or something and put them back up. And when you do that, you lose all this stuff. You lose fasteners and you lose siding, and sometimes you have to do it. There's no way around it. And early on in my career, I probably would have done a lot more damage to this building trying to understand it on the front end than I am now. And now I'm just looking at stuff like this, and I'm looking for the most efficient way to do it and the most surgical way to do repairs. So I think 9 times on this building we did a surgical repair like this, where it's a post and some sheeting, and you can kind of see it going around. And of course the hips failed. I mean, not the hip rafters, but the shingles, like that's where the water intrusion was. So the water goes down inside the hip. And we create models. On another slideshow I have this spins around really cool, but I don't think it does here. So we create these models, and this is the finished building.